Welcome to Tech Field Day, guys. This session is on NCS 5700 router, our new model in the series. My name is Vincent Ng, Technical Marketing Engineer for Cisco. Agenda for today. NCS 5700 is part of the current NCS 5500 series. I will first do a brief recap on the NCS 5500 portfolio, and then introduce the two new NCS 57 line cards. For investment protection and easy migration, we support both NCS 57 line cards and older line cards to run in the same chassis with compatibility mode. After migration is completed, we could run in native mode with more enhancements. We will do a comparison of these two modes. NCS 5700 introduces 400 optic support, and we will talk about the 400 optics available today and on roadmap. We will also introduce the concept of direct ports and flex ports on these line cards, and the flexible combinations of optics and breakout support on these line cards. Let's do a brief recap of NCS 5500. NCS 5500 was introduced more than 4 years ago and have a broad range of fixed and modular chassis form factors based on the Broadcom DNX family of MPU from Qumran MX, Jericho, Jericho Plus, to the Jericho II, which we'll be introducing today. This family now has 14 fixed chassis from 1 RU to 2 RU, and 3 modular chassis with 4, 8, 16 slots, and 11 line cards today, 9 of them based on Jericho and Jericho Plus, and 2 of them will be introduced today based on Jericho II. There is a key concept of base and scale versions in NCS 5500 for both fixed and modular chassis. The base version uses the internal databases on the NPU, such as LPM and LEM, for storing prefixes, MAC addresses, and labels. And these databases are currently fixed in sizes. The scale version has an external TCAM for additional route scale and increased ACL and QoS scale as well. There are 3 modular chassis available with many common components such as route processor, system controller, line cards, and power supply modules. Only the chassis itself, fan trays, and fabric cards are different for each chassis. For modular chassis, the line cards are inserted from the front horizontally, and the fabric cards and fan trays are inserted from the back vertically. And we can call this an orthogonal design. So you could see that in this diagram, different chassis requires fabric cards and fan trays with different heights. The first generation fabric card is based on the Broadcom AFE 3600 fabric chip. It is a cell-based fabric. It requires 6 fabric cards per chassis for full capacity and redundancy. It supports line cards based on both Jericho and Jericho Plus. It is a single-stage fabric and basically provides a full mesh connections to all MPUs on all line cards on the chassis. The design is very simple, and just one fabric ASIC for the 4-slot chassis, 2 ASICs for the 8-slot chassis, and 6 ASICs for the 16-slot chassis. So you can see that the only difference is on the height and number of ASICs. As we have mentioned, the fabric connections are very simple, and with full mesh connectivity to all MPUs on all line cards of the chassis. In this example, the 6 MPUs of the line card will be connected in full mesh to all 6 fabric cards, and we will step through the fabric connections one by one. 0, 1, 2, 3, 4, 5, and the full mesh connection is now completed. Right. We will now introduce the 2 new NCS 5700 line cards into the NCS 5500 family. A brief history on the MPU used in NCS 5500. The earliest fixed chassis and line cards are based on the Qumran MX and Jericho. And then we have many more fixed chassis and line cards based on Jericho Plus and a large LPM version of Jericho Plus. Today, we will introduce Jericho II. Jericho II is a new member of the DNX family from Broadcom. Based on 16-nanometer technology, it has 2 forwarding engines or cores per ASIC. Total performance is 2 billion packets per second, with 4.8 terabits network interface bandwidth and 5.6 terabit fabric bandwidth. This MPU is 400 gig optimized, so it is organized in units of 8 by 50 gig SerDes, which we call a PM50 or pod macro. Instead of fixed size databases such as LPM and LEM, as we have seen on Jericho Plus, the Jericho II introduces the concept of a single pool of resources called Modular Database, or MDB. It is capable of flexible allocation. We will have more details in the next section on Modular Database.
Hi, Vincent. How does the fabric bandwidth compare to previous versions, the 55 models?
Well, basically, your bandwidth, fabric bandwidth, has to support your network interface bandwidth. So, for example, if you look back to the previous generations, there you go on the comparison between network bandwidth and fabric bandwidth. So, for example, if you look at Jericho Plus, you see the network bandwidth 900 gig, and the fabric bandwidth is 1.2 tera.
Oh,
so it has to be large. It has to be larger.
Yeah,
because
it's a lot bigger.
There will be some overhead on the fabric, so you have to make some room for the overhead. Do we have further questions? And optionally, we could also support external TCAM. And the version supported by Jericho 2 is an enhancement called OP2. The OP2 TCAM not only can support higher route scale, it could also stored counters so that it can do additional statistics. Jericho II uses a new memory technology called HBM, or High Bandwidth Memory, for its external buffer. HBM basically stacks on top of the MPU package, and therefore it does not burn links on the PCB. HBM enables higher bandwidth with lower power consumption, and a total of 8 GB is supported and shared between the two cores. Jericho II also integrates 32 MB of on-chip buffer and 16 MB assigned to each core. As mentioned, Jericho II is 400 GB optimized with all 50 GB SerDes. It has 96 by 50 GB SerDes for network interface and 112 by 50 GB SerDes for the fabric interface. This is a chart on current Jericho and Jericho Plus performance. Jericho II has increased its PPS performance from about 800 million PPS to 2 billion PPS, which is about 2.5 times enhancement. In terms of bandwidth, Jericho II increases from 900 gigabits to 4.8 terabits, which is over 5 times better. As you may have noticed, the increase in bandwidth is higher than the increase in PPS, which is an optimization of the current trend of increasing packet sizes due to internet video.
So I think you're implying there that the size of the packet doesn't really matter.
The size of the packet, because the average packet sizes on internet is increasing, so for forwarding chip, it's better to optimize it for larger line rate packet sizes in order to fully utilize your bandwidth available on the chipset.
Okay, thank you.
This is a chart on current Jericho and Jericho Plus route scale. With Jericho II, without external TCAM, it could support roughly 2.5 million IPv4 prefixes, and it is larger than the 2 million prefixes of Jericho Plus with large LPM version. With external TCAM at FCS, Jericho II supports the same 4 million prefixes as the current Jericho Plus with external TCAM. However, we could support much higher scale in future IOXXR versions. Let me introduce the first Jericho II based LAN card, NC57-24DD. It is a base LAN card without external TCAM, and it supports 24 400 gig interfaces with QSFP-DD form factor on the front panel. We will talk more about 400 gig optic support and QSFP-DD form factor in the next section. It is using 2 Jericho MPU and therefore supports a total of 9.6 terabits throughput. And this is a line rate for all 24 ports of 400 gig. This line card requires an upgrade to the chassis for second generation fabric cards and second generation Fentries. This is already available for 8-slot and 16-slot chassis. The 4-slot chassis upgrade are on the roadmap. Total power consumption of this LAN card is about, say, 1,000 watts to 1,300. This is a simplified block diagram for the 24DD LAN card. It has 2 Jericho II NPU. Each NPU is connected to 12 QSFP-DD ports. Each port is having 400 gig bandwidth. This is a second NPU with 12 QSFP-DD ports. And both NPUs are connected in full mesh to the fabric cards, and we have shown in the previous example. So the 24DD LAN card architecture is very simple and basic. It is optimized basically for 400 gig operation. This is the second Jericho II based LAN card, NC5718DD-SE. As the name implies, the -SE meaning it's a scaled LAN card with external TCAM. There are 30 QSFP-DD ports on the front panel and support either 18 interfaces of 400 gig or 30 interfaces of 200 gig or 100 gig. It is using 2 Jericho II NPU and supports a total of 70.2 terabits. The external OP2 TCAM is used for additional route scale and statistics. It requires an upgrade for second generation fabric card and second generation fan trace, which is already available for 8-slot and 16-slot chassis. 4-slot chassis upgrades are on the roadmap. Total power consumption is about 1,000 watts to 1,400 watts.
Quick question for you on this slide. Looking at the first bullet point you have there about the different speeds that are capable and the number of ports that are able to be used, are you able to intermix it all with the 400 gig and then the 2 and 100, or is it all or nothing on one function?
There are a lot of combinations on this LAN card, which is more flexible than the 24DD LAN card. As this LAN card is more optimized for sub 400 aggregation with a mix of 400, 200, 100, and even break out into 4x25 and 4x10. We'll have a lot of examples in the next sections when we discuss about the 400 optics and breakout options.
All right, thank you.
Vincent, what about head-of-line blocking? Any problem here?
These two LAN cards are line rate, so there's no head-of-line blocking.
Okay, thank you.
So there's no oversubscription. Some other NCS 5500 models do have oversubscription, but not on this two LAN card. This is a simplified block diagram for the 18DD LAN card. It has 2 Jericho II NPU. There are 6 QSFP-DD ports connected directly to one NPU, so it has 400 gig bandwidth. And 12 flex port pairs, each port pair having a stacked QSFP-DD cages and connected to the NPU via a CDR with RGB or reverse gearbox functionality. The RGB CDR enables more flexibility in optics and breakout support. And as mentioned, we will have more details on this later section. It also has the external OP2 TCAM. And both NPU are connected in full mesh to the fabric card. So as you can see, the architecture of the 18DD line card is slightly more complicated than the 24DD line card, so it is optimized for more flexibility in its optic support and breakout configuration support. We'll have a whole section on this support. For these two, Jericho II line card require the second generation fabric card. This card is based on the Broadcom AV9600 fabric chip, or Ramon, which is a cell-based fabric. It only supports the second generation fan trace, and it has an incompatible connector with the first generation fan trace for protection against misinstallation. Both the second generation fabric cards and second generation fan trace are mandatory for the Jericho II line cards. The most important feature is backward compatibility with Jericho and Jericho Plus line cards. So we could mix all generations of line cards and operate on the same chassis. It is a single stage fabric and basically provides full mesh connectivity to all MPUs on all line cards on the chassis. Design is simple, again, just one fabric ASIC for the 4-slot chassis, 2 ASICs for the 8-slot chassis, 6 ASIC for the 16-slot chassis. So only difference is in the height. So let us compare compatibility mode and native mode in Jericho II. NCS 5700 has 2 operating modes. At FCS of iOS XR 702, we will support only compatibility mode, which we could mix Jericho II line cards with Jericho and Jericho Plus line cards on the same chassis. In future iOS XR versions, we will support native mode after all line cards are migrated to Jericho II or with new installations with only Jericho II line cards.
Is that an efficiency measure there? Is having everything the same Jericho 2 going to be more efficient in code version and memory consumption?
Actually, it's more from a features point of view. We'll see in the next slide about native mode enhancements.
And as well with that, then, is compatibility mode going away with the newer versions?
It's not going away. It will be in parallel for a period of time because a lot of customers we anticipated will be still using the current installations of Jericho and Jericho Plus line cards. We want to protect the investment.
So if they were upgrading line cards over a period of time, they would still be able to continue with the newer code then, correct?
Correct.
All right, thank you.
Yeah, so you already asked. It is to allow smooth migration of current NCS 5500 to higher bandwidth networks based on 400 gig. So you could protect your current investment on 100 gig while have an upgrade path to 400 gig. At FCS, compatibility mode provides feature parity with Jericho Plus, iOS XR version 6.5.1 for peering and core feature set only without layer 2 features yet, which is planned for future releases. But even in compatibility mode, there are some enhancements possible for the Jericho 2-based line cards, such as ACL permit counters without specific hardware profile, or egress IPv6 ACL now do not need recirculation. And BGP flowspec do not need recirculation. So these enhancements are there even in compatibility mode. Native mode supports only Jericho II line cards on the same chassis. It will provide all the enhancements possible for Jericho II NPU with appropriate future iOS XR releases. Some features under consideration are modular database profiles with flexible allocation, and we will introduce this concept in the next slide. ECMP FAC is now increased to 32K entries. It supports deeper label stack for segment routing and SRv6. There are more capabilities on egress passing and buffering for Jericho II. Jericho II support VXLAN and also peer multicast and possibly cloud-native BNG. So depending on
Do you know how
the
many labels for the SRv6?
can you repeat your question?
Do you remember how many labels it can support for SRv6?
I can't remember off the top of my head now. It's like there's an enhancement from the current label stack to the Jericho II. It's an increase of, I can't remember off the top of my head, but because it's haven't delivered and we're still in the drawing board, but we will announce it when it's available in our documentation.
Also, it is interesting to see here bit index explicit replication beer supports here, because I think Jericho 2 here, right?
Yeah, so this Peter here, can you hear me? So the label depth from program data you could support up to 14, but current SDK will be only support to 12. So when we launch in the native mode, the total label depth will be 12.
Okay. And beer support comes with this chassis, it seems, because Jericho chipset there, right?
Yes, only Jericho 2 is capable for beer. That's correct. Because the header length be the case. Yeah.
So do you remember how many bit string here it supports?
We could share offline, but we do have the data from the program to offer this one. We could keep it offline. But we did not top of my head. We could wrap it up a question later. Okay, and let me check.
Let's look at it. Sure.
Okay, thank you, Vincent. Go ahead.
More questions? I know this is an interesting topic. So all these again are in the drawing board. The hardware is capable to do a lot of stuff, and the software will have phase-by-phase released to support these features in our roadmap. Now let's talk more about modular database. We have mentioned that in current Jericho Plus, the internal databases such as LEM, LPM, and FAC are discrete and fixed in size. In Jericho 2, there will be a centralized pool of resources called Modular Database, or MDB, which allows flexible allocation of different resource types. So we're able to create profiles for different allocations for different use cases. Let's illustrate modular database concept with examples. This is an example for profile X, which requires more allocation of LPM. This is another example of profile Y, which requires more allocation of LEM. But you can see the allocation is from the same pool of resources. They're not fixed in their carving. So it gives us a lot of flexibility. For most users, they will be using a balanced profile with a balanced mix of layer 2 and layer 3 feature scale, such as IPv4, IPv6 prefixes, MAC addresses, amperage labels. But for layer 3 focused users, they could use an L3 optimized profile which increased LPM allocation, for example. And for layer 2 focused users, they could use a more layer 2 optimized profile with increased LEM allocation, for example. So this is the concept of modular database profiles for different use cases. Now let's talk about optics. The single most important innovations in 400 gig optics is the QSFP-DD form factor. It is based on the most successful form factor for 100 gig optics today, that is the QSFP-28. And we add a second row of pins to ensure backward compatibility with the vast amount of QSFP-28 optics already deployed today. It also enhances the SerDes speed from max 25 gig to max 50 gig, therefore supporting up to 8 links of 50 gig on the electrical interface. For 50 gig SerDes, it also uses the new PAM4 encoding and a better RSFAC 544514 for error correction. So with these innovations, we are able to support the newer 400 gig optics So I pressed the slightly wrong button. So with these innovations, we're able to support the newer 400 gig and 200 gig optics, as well as all previous generations of 100 gig and 40 gig optics. Furthermore, different combinations on the number of SerDes plus the SerDes speed give us flexible breakout options for different types of optics. To illustrate, QSFP56DD can be broken out to 2x200, 4x100, and 8x50. QSFP28DD can be broken out to 2x100 and 8x25. QSFP56 can be broken out to 2x100 and 4x50. QSFP28 to 4x25. And QSFP Plus to 4x10. Finally, QSFP-DD support much higher power consumption. So for future optics, which may require power up to 20 watts, such as 400 gig ZR and ZR Plus coherent optics, and the 100 gig ZR support. On the optical side, there are a whole new generation of 400 gig optics standard, both from IEEE and from MSA. Starting with 400 gig optics, instead of the current 25 gig wavelengths with NRZ encoding, it is migrating to 50 gig and even 100 gig wavelengths with PAM4 encoding in order to lower the number of lasers and complexity of the optics. Let us start by categorizing the cable types, such as copper AOC cables, multimode cables, and single mode cables. And each category may also have parallel or duplex optics. For passive copper, we have cables to about 3 meters. For active copper, we have cables to about 7 meters. And for active optical cables, we have cables of about 30 meters. For multimode optics up to 100 meters, we have SR4-BD running on 4 pairs of bidirectional fibers, and SR8 on 8 pairs of multimode fibers. These two optics are parallel optics, meaning they could support breakouts. So the SR4 BD supports breakout to 4 by 100 gig BIDR, and the SR8 support breakout to 8 by 50 gig SR. For single mode optics, the DR4 supports up to 500 meter. This one is also a parallel optics, and therefore it can be broken out to 4 by 100 gig -DR, FR, or LR, but limited to 500 meter. Please note, this breakout requires 100 gig wavelengths optics on the other end. If you did break out to longer distances, there are the 4 by 100 gig FR and 4 by 100 gig LR for 2 kilometer and 10 kilometer respectively. And these optics are designed for breakout applications.
What were those distances again, Vincent?
As you can see from below, it's 500 meter, 2 kilometer, and 10 kilometer.
Oh yeah, I see it. I'm sorry. Thank you.
All right, for duplex optics, we have 400 gig FR4, which support up to 2 kilometers. This is based on CWDM technology of multiplexing 4 wavelengths in a single fiber. For 10 kilometer, we have 2 versions. The first one is 400 gig LR8. Second one is 400 gig LR4. The LR8 is based on LAN WDM of 8 wavelengths. And the LR4 is using CWDM of 4 wavelengths. The LR8 will be available earlier, but we expect the LR4 will be cheaper when it comes out. For 40 kilometers, 80 kilometers, or beyond, we will need the 400 gig ZR or ZR4 standard, which are coherent optics. These are still under development, and please refer to our other Cisco Live presentations on 400 gig coherent optics. These few optics are already available in 702, and others are still on the roadmap. So there are a lot of optics coming on the 400 gig side. And another aspect of it is, in some current deployments, there are a lot of current generation 100 gig optics, which is still using 4 by 25 gig NRZ wavelengths. So there's a need for higher density support of these optics in the new LAN Card. These optics are available in QSFP28 DD form factor, supporting both multimode fibers and single mode fibers, and they can be parallel or duplex. For multimodes up to 100 meter, we have the 2 by 100 gig SR4, which contains 2 instances of 100 gig SR4 optics in a single QSFP DD form factor. For single mode up to 500 meter, we have 2 by 100 gig PSM4, which contains 2 instances of 100 gig PSM4 optics in a single QSFP DD form factor. These two are parallel optics with 4 pairs of fibers each. So we require a high density connector on the QSFP DD front plate. And we have chosen the MPO24 for that. For single mode fibers up to 2 kilometer, we have the 2 by 100 gig CWM4 And for duplex optics up to 10 km, we have the 2 by 100 gig LR4. These two are duplex optics, but again, the QSFP-DD faceplate cannot fit the two duplex LC connectors. So we have chosen the more compact dual duplex CS connector. The 2 by 100 gig LR4 is already available, and the rest are on roadmap. And as we're migrating for 225 gig wavelengths to 100 gig wavelengths, we will need a new generation of QSFP28 100 gig optics supporting 100 gig wavelengths. These are mostly available in single mode fibers and duplex option. In this category, we have 100 gig DR for 500 meter, 100 gig FR for 2 kilometers, 100 gig LR for 10 kilometers. And for 80 kilometers and beyond, we will require another category of 100 gig ZR coherent optics, which are usually in QSFP-DD form factor instead of QSFP28, because we need higher power consumption for these coherent optics. All of these optics are still on the roadmap. This is a quick example of 400 gig DR4 breakout. Please note, this requires a new generation 100 gig wavelength optics on the QSFP28 side, such as the 100 gig DR. The DR4 optics uses MPO12 connectors for high density 4 pairs of single mode fibers. And it connects to 4 duplex LC connectors on the other end. It will also interrupt with 100 gig FR or 100 gig LR, but limited to 500 meter. This is a comprehensive table for 400 gig optics roadmap for the NCS 57 LAN card for your reference only. And we are not going through them in detail now due to time. Please note that some of them are already available at FCS in NICSAR 702, and others are on the roadmap. Let us introduce the concept of direct port and flex port for the two Jericho II LAN cards. On the 24DD LAN card, all 24 QSFP-DD ports are connected directly to the Jericho II MPU, supporting 400 gig bandwidth individually. So each QSFP-DD connectors connect to an octet of 8 by 50 gig SerDes on the Jericho II, which is also called a PM50 or port macro. On the 18DD LAN card, 6 QSFP-DD ports are connected directly to the Jericho II MPU, supporting 400 gig bandwidth individually. And then 12 flex port pairs, each with QSFP-DD stacked cages, are connected to a single Jericho II PM50 and sharing 400 gig. Each port pair is handled by a CDR5 with RGB or reverse gearbox functionality. This CDR allows a more flexible combination of 400 gig and lower speed optics and breakout options. Let's discuss for direct ports, each with individual 400 gigs, the possible optics and breakout options. Of course, it will be subject to appropriate optics availability and software releases. For QSFP-DD 400 gig optics, it can be broken out to 4x100 and 2x200. For QSFP56 200 gig optics, it can be broken out to 2x100 gig. For QSFP28DD 2x100 gig optics, each individual 100 gig optics can be broken out to 4x25. For QSFP28 100 gig ports, it can be broken out to 4x25. For QSFP plus 40 gig optics, it can be broken out to 4x10. So the support for the direct port is rather straightforward. Now for the flex port pairs. It is sharing 400 gig for the two QSFP-DD ports. So it is optimized for sub 400 gig aggregation, and it allows a higher density of low speed optics and more combinations of breakout options. Of course, again, subject to availability of the optics and software releases. There is a dependency on N and N+1 ports on the flex port pair. If port N is using QSFP-DD 400 gig optics, it can be broken out to 4x100, 2x200, but port N+1 must be empty because the 400 gig bandwidth has been used already. If port N is QSFP56 200 gig optics, it can be broken out to 2x100 gig, and port N+1 can also be a QSFP56 200 gig optics. So you can see in this combination, we support two optics sharing a single 400 gig port on the Jericho II. If port N is QSFP28DD 2x100 gig optics, port N+1 can also be a QSFP28DD 2x100 gig optics. Therefore, in total, we support a maximum of 400 gig optics, which is the older generation 4x25 gig NRZ optics, and it's very useful for current deployment. We have a lot of old generation type optics. If you have a lot of breakout, and port N can be using QSFP28 100 gig optics or QSFP plus 40 gig optics, each capable of breakout into 4x25 or 4x10. Port N+1 can also be in another QSFP28 or QSFP plus optics doing breakout. So in total, you could have up to 8 low-speed breakout ports on a single Jericho II interface. So as you can see, the 18DD LAN Card gives you much more flexibility in terms of lower speed aggregation and breakout. Let's do a more detailed illustration. This slide will illustrate the operation of 400 gig mode in the flex port pair. The CDR is operating in retimer mode without reverse gearbox. The 400 gig optics, after inserted into the QSFP-DD cage, it will be using the 400 gig AUI-8 8x50 gig electrical interface. The CDR will connect these 8 SerDes from QSFP-DD to 8 SerDes on the Jericho II PM50. Jericho II, we use the same 8 by 50 gig with 400 gig AUI-8 interface, and it will utilize one instance of 400 gig MAC. So in this case, one PM50 macro support one 400 gig optics. This is the basic use case. The CLI for this mode is shown here. And the other port must be empty because you already use up the 400 gig bandwidth. This slide shows the CLI. And after you apply this hardware module port range command, you can see that it automatically generates a 400 gig interface in software. Now we look at a more complicated example with the flex port pair operating in 2 times 100 gig mode. The CDR in this case is operating in reverse gearbox mode. The 2 by 100 gig optics, after inserted into the Kawasaki DD cage, it will generate 2 instances of CAUI-4 electrical interface. Each is 4 by 25 gig. For the first instance of 100 gig optics, the CDR will use reverse gearbox to convert the 4 by 25 gig CAUI-4 interface to 2 by 50 100 gig AUI-2 interface on the Jericho II. And the Jericho II will also generate one instance of 100 gig MAC. So this is the first instance of 100 gig optics. For the second instance of 100 gig optics, the same process will repeat. Reverse gearbox into Jericho II, 100 gig MAC. And then when you plug in the second Kawasaki DD 2 by 100 gig optics, it will be using 2 more instances of CAUI-4. And the same process will happen with the third instance of 100 gig, reverse gearbox to Jericho II. The fourth instance, reverse gearbox in the Jericho II. So finally, we have 4 instances of 100 gig AUI-2 on the Jericho II, and 4 instances of 100 gig MAC will be generated. So in this mode, for single Jericho II PM50, it is supporting 4 by 100 gig interfaces. The CLI for this mode is shown here. And you can see from this slide, after you commit the hardware module port range command with mode 2 by 100, 4 instances of 100 gig key interface will be generated. Well, we're coming to the end of our presentation. This is normally a PM slide, so I'm not going to elaborate on this, but in conclusion, ANSYS 5700 provides higher capacity, higher density, and it provides TCO savings and investment protection. I think we welcome questions now. We still have about a few minutes left.
Yeah, just one quick one. What's the positioning of the NCS versus the ASR in the service provider market?
Peter, you'd like to take that?
Yeah, absolutely. So you probably talk about ASR, right? So I'm sorry, the question, the NCS with the what, ASR? Or?
With the ASRs.
Okay, so you probably mentioned this ASR 9K. So ASR 9K is still positioned for the edge portfolio. The NCS 5500, 57 is continuing to drive the core peering aggregation. So I think from the application-wise and overall scalability in conjunction with the scalability, ASR 9K still have the rich portfolio, especially we have the Lightspeed Plus. So Lightspeed Plus just launched approximately half a year ago. So this portfolio will continue to help to drive another 2 to 3 years on ASR 9K for edge. Having said it, because I think there's one summary table, you see the Vincent show here. There's some feature probably have a certain overlapping when the Jericho II able to catch up the scale and feature functionality. So lot position-wise, right, we still maintain the same. The NCS 5500 will be the core peering, high-scale aggregation. ASR 9K still be the edge. But again, what I'm saying, it really up to customer to decide, right? If you have a certain overlapping, definitely, if the functional scale fall into that category, that will be okay. Yep.
So right now we're looking at the NCS at the edge, the ASR 9K at the core. Are you eventually looking at the idea of the NCS being the whole portfolio, or is that split strategic?
I think right now we still try to split strategically. Yes.
Okay, thanks very much.
Yeah, no problem. And I just checked, right? The beer is 24K beer ID from the Broadcom data sheet. So you need to keep in mind, right? When Broadcom say 24K, it's not direct associated with when we launch will be 24K, because you need to also depend on the SDK readiness, software development. So from the hardware wise, the beer set is the beer ID total 24K. This is from hardware resource. So when we implement, we'll give you the more detail from the overall scale able to support.
Cool, thank you.